The third type of spectra that we're going to talk about is called fluorescence spectra. And this is probably the most complicated form of spectra that we'll see. And we're not going to actually really do any calculations with it, but we want to make sure that you kind of understand the basic process because, well, this is what happens in your fluorescent lights. So, what we see is a new spectra that's produced by fluorescence. And a typical energy versus distance graph that we'd see for a molecule that fluoresces looks something like this. And we're going to spend a little bit of time going over this, but what we're going to get is we're going to get these different energy levels. And as I said in the previous one, the atomic spectra, or the atomic energy levels, will look something like that. We have its individual levels that goes through. Well, what we saw before is that we can absorb in there, and then if we radiate back down, we get a color. If we absorb up, say we absorb up to here and get radiated back down, we get a different color. Well, what happens in fluorescence spectra is that when we absorb in, sometimes we decay down. When we decay down, we can decay through vibrational relaxation or a bunch of other processes. And these processes may not actually radiate light. They may give off their energy in a non-photon sort of way. And one of the ways that this can happen is what we call a phonon, or a bit of sound. We can cause a system to essentially produce a little bit of noise. And there's other non-radiative, what we call non-radiative processes. But what we're really concerned is that what we absorb our energy in, we can decay to a different energy and decay down. And this would normally give us a different color, similar to the electron spectrum. However, most of these molecules that fluoresce are much more complicated than the hydrogen atom, which has just electronic levels. Each one of these lines may have, there might be different vibrational lines, there might be even different rotational lines. And as you add more of these in, this could be one atomic level. This would be another atomic electronic level. So in here, the electronic level, this would be an n equal 2 case. Inside the n equal 2, there might be a half a dozen vibrational states that can happen. In each one of the vibrational states, there could be a half a dozen to a dozen rotational states. So not only do we have to worry about what is the electronic level, but also is the molecule vibrating? Is the molecule rotating? And each one of these have different characteristic energies. So when we go up, we absorb up, we can decay non-radiative down to some other excited state. Our ground state is here, but this would be an excited state. When we decay down to a different color. So certain colors that may not have been visible because of just pure atomic or electronic transitions can now become visible because we're looking at different colors. And we get a lot more of these colors because of all these different things, these vibrational or these rotational. And this definitely is getting into the whole realm of quantum mechanics. And this is a little bit of complicated stuff, but it's not too horribly difficult to understand. And if that's not even worse, we can actually get where the two different molecules can actually interact, and you can cross energy from one to the other. So kind of like elastic collisions, you can give one energy to another one. Two molecules can bump into each other, and if they're different molecules, they may be able to have the same energy at one point, so we can transfer energy from one to the other. This guy will go to 0. Now this guy's excited, and it can decay to something else. So a lot of different things can happen with this, but fluorescence gives us a different type of color. Now the two things to kind of think about is the main difference between fluorescence and atomic spectra is the whole concept of non-radiative decay. And the other thing is, when we look at, say, the fluorescent lights, because they're produced in a kind of similar way than that atomic spectra are, they are a little bit more discrete in energy and not as smooth as black body radiation. And that's why when you look at fluorescent lights, the fluorescent lights have a different look than the black body radiation, or the incandescent lights, the light bulbs with filaments. And that's why a lot of people don't like fluorescent lights, is because their spectra does not look natural. It looks in a different thing, and really it's a different physics process that causes it. So when you're looking at the sun, you're looking at black body. When you're looking at fluorescent lights, you're looking at the light that's caused by a fluorescent process. And that's why the two, even if they do produce visible light, why they look different. It's because their spectras are produced in a different way.